quick recap of what we were doing. So essentially what we wanted was a very simple model of a neuron and something which essentially had these three properties, okay. So that it had a binary kind of states, a resting state and an excited state. It went from a resting state to excited state if it was stimulated beyond a threshold, and finally there was a recovery period during which if you try to stimulate it with whatever stimulation that previously caused an excitation, it will not show any response, okay. So you have to wait for it to recover before it can respond again. And as we found that we can do this very simple model where you can first write down some variable, dynamical variables. So I was using x in the previous lecture, so because it doesn't matter at all what you call it, here I am calling it u, but it's the same thing. It's basically a variable which is representing the state of the neuron at any given time, and I want to write down a du dt, a rate of change of u, as a function of u, okay. And so what are the things I know? I know that there is a resting state, and since it doesn't matter what the origin of my scale is, I can set this to 0. Then I need to specify my excited state. Oh yeah, so this is supposed to be a stable state. So if you give it a push, so if it's 0 plus something or 0 minus something, small amounts, then it should go back to 0. So the resting state is a stable one. So that's why the arrows should point towards 0. Then you have to specify an excited state. So again, for a scale, once you set the origin, you can, the markings that indicate like what is the unit, that also you are free to choose, okay. So in this kind of a scale, we are using 1 to indicate the excited state. And again, sorry, what did I do? Yeah, so again, if you perturb it slightly from the excited state, it should not go over somewhere else. So again, it should be locally stable. And now the threshold, which is of course a value that you can't independently choose, because now you have set your scale by fixing the origin and the unit. So in those units it's called alpha, okay. So typically it's between the resting state and the excited state, because if it's less than the threshold it will go to the resting state, if it's greater than the threshold it will go to the excited state. And so now it divides the flow between those initial conditions which will flow to the resting state and those initial conditions which will flow to the excited state, okay. And I said, okay, what is the simplest functional form for f which will satisfy this? And as some of you actually pointed out, that this is essentially going to be a cubic polynomial, okay, because it has 3 roots and it guarantees that here the rate of change of u with respect to time is positive, and so therefore it satisfies that the flow will go from negative values to 0, that means it increases. Here du dt should be negative, and so this satisfies the fact that flows should decrease in value, the flows should go such that u decreases in value from something close to alpha towards 0 and so on. So each value of du dt at every point should be consistent with the flows that I have here, and the cubic polynomial is the easiest function which gives you this, okay. But then we are stuck with the problem that once you go here you are stuck. So this is what typically is called a bistable system, okay. That is, you have 2 states, both of which are stable, and depending on initial condition you can go here and stay, or you can go here and stay, okay. So a typical bistable system would be, for example, I don't have a flexible thing here. Okay, imagine one of those metal rulers, okay. So if I press it down very hard, it buckles, but will it buckle towards the left or will it buckle towards the right, okay. Both are equally likely, okay. Which one it will do, go to depends upon the exact way in which you push it. Maybe there's slightly more pressure towards the left than right, and so it buckles towards the left, and so on. So very small variations will decide whether it will buckle to left or to right. But both of these are equally stable, and so you've got a bistable system if you push down on the ruler hard enough. Okay. I'm sure there are easier examples to think of, but right now I can't think of any. Oh, hold on, a switch. So if you take an electrical switch and you push it, it will go to the on state and it will stay there. If you give it sufficient pressure, it will go to the off state and stay there. Okay. So that's also a bistable system. All right. So now I need some way in which once it has reached the excited state, after some time it will eventually come back to the resting state without you having to do anything. So it should do it automatically. So how do you do it? Well, one way is to actually introduce a negative quantity to the right of this equation. So if you introduce a negative quantity, what happens is, that means you are taking this curve and you are pulling it down. So if you had added something, you would have pushed it up. Okay. So if you pull it down or if you push it up, what happens? So let's first see if you had pushed it up. So instead of minus v, suppose it was plus v, v being positive, then you would have pushed it up. And so now you notice that it cuts the 0 axis where du dt is 0 only at one point, namely at this high end. Okay. So basically you only have an excited state. What has happened here is that as you gradually push it up, the alpha and the 0 approach each other, or the resting state and the threshold approach each other, and at some value of v they would collide, and this collision leads to their mutual annihilation, and after that there is no more fixed points here, the only equilibrium is over here. Okay. Conversely, if you have a minus v, you basically pull it down, and so this one and this one, these two equilibria approach each other, annihilate, and then eventually go away altogether, so that you are left with only one equilibrium at the lower end of u. And so you are left with something close to the resting state. And then once you have reached, so basically this ensures that because there is no equilibrium here, if you are here at any point of time, once you have pulled it down further enough, it will be forced to come over here, and once you have reached this, you just let the curve relax back to its original point, and because the equilibrium has shifted, your state will also shift towards u equal to 0, and you have gone back to your resting state. Okay. So that means this v is not a constant, but itself is changing with time. So I need to write down a differential equation, and the simplest differential equation I can come up with looks something like this. So it is positively proportional to u, because when u is high, that is when you are in excited state, v should be large so that you can pull it down sufficiently below that this and this disappear. Okay. So that is why it has a k into u. K is just a constant of proportionality. But once you have reached here, then you should make it relax back to the original case where v was 0. So that is why you have a minus v term. So when u is very close to 0, is this minus v term that will dominate, and dv dt equal to minus v ensures that actually you will go back to 0. So in case that is not immediately obvious to you, there are two ways you can do this. Either you can actually try to solve it, okay, but there is an easier way. We just plot v dv dt. So how does this look here? Straight line, yeah, negative slope, correct. So sorry, my hand is betraying me. Yeah, okay, it goes through 0. Okay. Now what will be the flows? So you have done previously, I have given you flows and you have drawn the functions. Now I have given you the function and I want you to tell me the flows. So which way will so if you are here, which way will you move? Will you decrease or will you increase? See, if you do like this from my end towards 0, right, because it's positive, right, so the value will increase. Okay, here it's negative, so the value will decrease. So basically you will move towards 0. Okay. If you are mathematically inclined, of course you can do it in a different way. So you can say, okay, dv by dt equal to minus dt, you integrate, so this gives you log v, then constant minus t, and so then you take exponentials on both sides, and so you get v is some constant e to the power minus t. Okay, and so basically this tells you that if you look at v versus t, it will exponentially flow towards 0. Okay. But a graphical way of doing this is much more elegant. Okay. Okay. So yeah, and last but not the least, where do I get the recovery period from? Well, this process takes place much longer than this process. Okay, and so therefore this will change very, very slowly compared to this. So how do you ensure that? You multiply that entire right hand side with a factor epsilon, which is much, much less than 1. Okay, so this, if you call this time scale at which this happens to be unity, then compared to this time scale is very slow, and so that's epsilon times slower than the time scale that you are talking about here. So epsilon, so if you are following a dimensional analysis, so what you can do is you can say that, okay, dv dt is equal to epsilon ku minus v. Now this has the same dimension as v, and you have to have a, to be consistent with the left hand side, this has to have unit of 1 by time. So this is basically a rate. Okay, it is 1 over time, and this time is basically the recovery period or related to the recovery period. So if you want a very slowly recovering neuron, you just make epsilon even smaller, like 0.001 or something.
You have the same dimensions?
No, they need not. Okay, so first of all, this is just a phenomenological model. Okay, right. So if you relate u to voltage, okay, then you have to ask what is actually v. Okay, so if it's like something like conductance, so k will have to have such a dimension such that k into u, so k into a voltage will give you a conductance. Okay, but this part I am not tackling at all, because Pranay is doing the Hodgkin-Huxley. The best way to see this is basically take Hodgkin-Huxley and do a simple reduction in which you go from 4 variables to 2 variables. Okay, and so what you will see is that the first, the u variable is actually the same as Hodgkin-Huxley's v, transmembrane potential, but the v over here, small v over here, that's unfortunate notation, sorry, I shouldn't have called it v for confusion. It's actually related to one of the gating variables which Pranay showed. It's actually the potassium channel gating variable. Okay. Now it's hard to see, I agree, without actually explicitly showing you this. Okay, but in that notation it will become unitless, v will become unitless actually. Okay, in some other models sometimes this is taken as a conductance. Okay, the v is taken as a conductance, so it depends on which model you follow. But in our world of just coming up with a model which will exhibit the basic properties, it does not really matter too much. Okay. Just enough to say that, look, this part must have the dimension of v because it is ku minus v, and so if it has to be consistent, this part has to be consistent with this has to have the unit of 1 by time. That is sufficient. Okay, now phase plane analysis. So I am not sure whether Pranay will cover phase plane analysis. You will. Okay, so this, so whatever Pranay will be doing, you can also do this with this much simpler system. Okay, so what is phase plane? Okay, so let me first give you an example from something which you should be all familiar with, a simple harmonic oscillator. Anyone remember what's a simple harmonic oscillator? A spring attached to a ball or a pendulum undergoing some small amplitude oscillations and so on, right? So yeah, so let's take this spring attached to a ball. Okay, Okay, so you have a spring which is connected to some mass, okay, and the spring has a stiffness constant K. Okay, that doesn't matter actually. Okay, so we use Newton's law. Okay, so we say what is the force, restoring force? So if you stretch the spring very hard and let it go, you know that this will bounce back, right? So that means there is a force acting in the direction opposite that of the displacement. Okay, so you are displacing it and there is a force which is pulling it back, right? So Newton's law says that the force is equal to mass times what? Mass times acceleration, right? So if I call x to be the displacement from its equilibrium position, so let's call this equilibrium position, that is when the spring has no extension or contraction. So you pull the spring, you have pulled the spring by this much, okay. So now the position of the spring has shifted by this much. So you call this variable x, by how much it has been pulled from the equilibrium, okay. So this extension is now causing a force to act on this thing which is trying to take it back, okay. So what is the, if you have x as the position coordinate, what is velocity? It's the dx dt, it's the first derivative with respect to time, it's the rate of change of displacement with respect to time, right. What is acceleration? Is the rate of change of velocity with respect to time, right. So it is d dt of dx dt. Everyone with me so far? If it's problematic, just ask me. So this is equal to m second derivative of x. Okay. Everyone with me? Or if there's any doubt, just ask me that, you know, what is this? I don't understand this. Complete poker faces everywhere. Okay. So, all right. Now, anyone remember what is the restoring force for a spring? Sorry? Minus kx. Yeah. So, therefore, I can write it as, okay. So, this is my simple harmonic oscillator. No, x is a displacement, right? So, in my convention, this is positive and that is negative. Okay. Sorry? No, but my left and right. So, if I, sorry, not left and right, down and up. So, depending upon where my x naught is, so if it's moving this way, that means it's moving in the positive direction. If it's moving this way, it's moving in the negative direction, for example. Okay. So that's convention, but I need a vector to indicate which way is it moving. Is it moving from top to bottom or bottom to top? That's why. And the restoring force is always working against the direction in which it has been stretched or contracted. So if it's contracted, the force is pushing it back to the equilibrium. If it's stretched, the force is pulling it back towards the equilibrium. Okay. Without the vector, you won't be able to make sense of that. Okay. Okay. Anybody else? Any questions? Okay. Now, this is how you normally see it in your +2 textbook, or if you're preparing for JEE, whatever. This is how you see it. In a dynamical systems perspective, we always reduce everything to first order differential equations. The reason being, we are interested in the phase space, and in the phase space, the dimension of the phase space is given by how many equations you have which are all first order. Okay. So the relevant variables here are actually position, which is x, and velocity, or you can also, so this is v, or equivalently you can talk about momentum, which is p equal to mass times velocity. Okay. Now, why do I write it in this way? Because now I can write that equation in terms of two coupled first order differential equation. So, first I define my momentum. So, what is momentum? So, P equal to m times dx dt. Okay. So, this defines a first order differential equation. Okay. Now, my second differential equation would give me dx dt. Oh, sorry, this is already dx dt. Yikes. So, so now I need a equation for dp. So, dp dt. So, what is dp dt? Anyone? Yeah. So, you already know what the force is.
Minus.
What is that? Sorry, louder.
Minus k.
I heard
Minus
some
k.
minus kx. Yeah, and some whispering from the back. Yeah. If you're not sure about it, please do ask. Right. So I can also rewrite this as, so I can divide by m on both sides, and so I can write it as p by m. Okay. So now notice I have an equation in differential equation in x, and I have a differential equation in momentum. So these are both first order. Okay. What's the advantage of doing this? So now I can actually show the motion of the simple harmonic oscillator in the phase space, which is defined by, whose axes are basically the variables whose first order differential equations I am looking at. So, x and p. Okay. So, what I am going to do is I am going to create a coordinate system. So, this is 0 0. Okay. Now, what is the behavior of the system going to look like in this position momentum space? Anyone? You know how it looks like in time, right? You know that if I look at x versus e. So, if I look at x versus t, then starting from somewhere here, it will look like a sinusoid. Okay. If I plot p using red color, what do you think it will look like? So, suppose this is the maximal extension. What is the momentum there? 0, right? And so it will look like this. Sorry, okay. So now can you tell me what it's going to look like in px space? Yeah, it's going to be a closed curve. Okay. So it's going to, let me see if I've got another color. It's going to be an ellipse. Okay. Everybody understands why? Okay. So let me start. By the way, I mean it looks very asymmetric when I draw it in this way, so I'm not a very good systematic pin draw. Okay, let me draw it such that it looks better. Now it looks a bit more symmetric, right? Okay. Okay. So let's see. How do we analyze this? So at this point, x is what? 0, right? So that means I am back in the equilibrium, but I've got a positive momentum. Okay. So if I say that my direction, positive direction is downward, so that means I'm basically on my way towards the expansion. So as I expand, I eventually come here where I've reached the furthest stretched point. Okay. So this is x naught, and this has now expanded the most. At this point, my velocity has gone to 0 because I'm about to return back, and so my p is going to be 0. Okay. At this point again, so now it's going to be returned. Okay. So it has gone back to equilibrium, okay, but it's on the way to the compression, and so finally here it has reached the most compressed state, and so this is your x naught and this is the most compressed state. Okay. Now velocity has reached 0, and so after that it will again keep going back. So that's why you will have a closed curve, and each point can be associated with a particular configuration of the mass and spring system. Any confusion? Yeah.
Have a negative and a positive.
Yes. So that's why I said 0, 0. So this is positive x, this is negative x. So this means that are you below the equilibrium or are you above the equilibrium point? Oh, sorry. What did I do? Let me just try to think. Sorry, I think I just completely flipped it around, right? Yeah, sorry. This is yeah. So this is p equal to 0. So let me see. Yeah, sorry. This is I flipped around the whole convention because I said it's moving downward. So sorry. Thanks for pointing that out. So according to this convention, this will be compressed. Thanks. So this will be compressed. This is x naught. This will be stretched. Okay. And so that means here it's actually which way? So this is x naught, and if I'm moving in this way, so then I'm going to go downward, and here I'm going to move upward. Okay. Is that okay with you? No? Oh, okay. Sorry. What did I say? Yeah, sorry again. So the convention was going downward is positive, right? So here it's negative. Yeah, sorry. That was correct. I mixed up. Thanks for pointing it out. Okay, is everybody okay with me so far? Now that your friend has corrected me? Okay. So the convention is down is positive. Yeah. Okay. So the convention is going down is positive. Okay. This part is positive, this part is negative, right? Now in this axis, this is the positive part, this is the negative part, okay, for x, and this is the positive p, this is the negative p, right? So as by convention, my positive momentum is when you're going downward. That means when you are at the highest value of p, you should have reached equilibrium but have the highest velocity going down. Okay. So that's why you're moving down. So you're basically you have reached the, so think of it like this. So you are moving like this. So equilibrium, okay, you're so like this, then you're stretching like this, reach the highest level of stretching, and then you're contracting. Equilibrium, going down, contraction, expansion, equilibrium, contraction. So you're going like this essentially. So you can even specify an arrow. All right. Any questions? Yeah. No, the equilibrium is halfway between the completely expanded and completely contracted. So these are the equilibrium positions which corresponds to x equal to 0. This is x and this is the 0 position. Okay. All right. So now let me do this with Fitz-Nagomo. Okay. So how will you do this with Fitz-Nagomo? So here I had the luxury that I could draw x versus t and p versus t and could show you. Okay. In general, for dynamical systems, you want to do this without having the plots of the dynamical variables as a function of time. So how will you do it? So what we do is we take the first order differential equations and we draw the curves where you set du dt equal to 0 and dv dt equal to 0. So this gives you what are known as the null-Klein curves. Okay. So remember what du dt was. Du dt was u into u minus alpha 1 minus u minus v. So I want to know what is the curve on which du dt is 0. That is, anywhere on this curve u will not change with time. Okay. So if I set this equal to 0, this gives me equal to v equal to u into u minus alpha 1 minus u. Okay. So now I can go back to my phase space and this is u, this is v, my two phase space coordinates, my two variables. So how will this look like, this curve? V equal to u into u minus alpha into 1 minus u. What is it? Same as in cubic polynomial, right? So let me plot it using red. So it has three roots. Huh? Yes, because notice it has three roots: u minus 0, u minus alpha, 1 minus u. Those are the points at which v is 0. 0, alpha, 1. Okay. What about the null-Klein for? So this is called the u null-Klein, that is du dt equal to 0. Okay. Now I need the v null-Klein. Sorry? V is the variable because that v treating v as a constant is long gone.
It has three roots when this entire thing equals 0, right?
Yeah, so notice what I have done. This is a
Okay,
variable,
okay,
this is another variable. Okay.
I was
Otherwise, if this was a constant, right, I wouldn't even have a two-dimensional system if that was a constant, right?
Yeah.
Okay, so now what is my dv dt? dv dt is epsilon ku minus v, right? So what is the null-Klein?
Just the straight line.
It's a straight line, right? You set 0 equal to epsilon ku minus v, which is simply v equal to ku, right? So depending upon what is k is the slope, it will look like this, or it can also, for example, look like this. But if it's like this, you're in real trouble. Okay, that's not going to behave like a neuron. Okay. Now what it will behave like is a question I leave to you. It's a homework question. What will happen if k is small enough such that it intersects not only at 0 but also at other 2 points.
It won't have an effect.
Sorry,
It won't have an effect.
it's worse than that.
There will be two more points with exit stable.
0 is a stable point,
There will
and
be two more points that will exhibit position where V won't change, and then you will have
yeah, but not all of them will be stable.
but
Okay, so you have 3 equilibria, 2 of which will be stable.
the highest one will be stable. So once it gets excited,
So basically, you will go back to being a bistable situation. Okay. So this is your V null climb, dV dt equal to 0. Okay. All right. So how do I now find out what the trajectory will be?
take the derivative. Like you have du by dt and du by dv by dt. You take the ratios and find du by dt if you want slope of
Yes. But like this is a much simpler way to do this. Just graphically. Okay. Remember, math with pictures.
then we can just take the point, plot them, and how changes.
No, you already know the stable point. There's only one equilibrium, right? Okay. So to find out what your trajectory would be, you find out that at each point, which way would you be flowing? Okay. How do I do that? There are two variables, right? U and V. So find out which way would the U be pointed? Would it be pointed towards the left or the right? And which way would V be pointed? Left, up or bottom? Okay. So here, see, this line divides the region where du dt is positive from the region where du dt is negative. Okay. So in this region, is du dt positive or negative? Yes. How many think it will be negative? Okay. Harish is like betting his thing on it being negative. How many think it will be positive? In this blue point.
It's positive only. It's going up.
Sorry, what is going up?
So the U,
Yeah.
you have positive du dt, right?
No. So the question is, what is du dt here? Because du dt is 0 here. It could either be positive or negative, right? Because it separates the region where du dt is 0 positive from du dt is negative. So the question is it positive or negative?
Positive.
Positive. Okay. So Harish thinks it's negative and Akshay thinks it's positive. Who is in team Harish and who is in team Akshay? Sorry?
Negative.
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 Sorry? Negative.
Negative.
Okay. Harish sometimes harries his fans actually. Let me warn you. He acts as an agent provocateur. So if you actually think about it a bit, what is this region? Okay. So here, this means that whatever is going to be true here is also going to be true here, right? Okay. Okay. So here, if you are here, which way should you go? Towards 0. Right. So what is it going to be? Negative. Yeah. So here du dt is actually negative. So by trivial argument, because the whole region is being separated by the du dt equal to 0 line, here du dt will be greater than 0, which is consistent with what we already know. Okay. What about the V null climb? So here everywhere the u arrow, that is the horizontal coordinate arrow, would be pointed this way, and here everywhere it will be pointed in this way. Okay. Okay. What about the V arrow? So that means this part separates a region which is dV dt is positive from dV dt negative. So here, what will it be? dV dt positive or negative? Sorry? I heard some positive, some negative. So who's betting on positive? Okay, some people are becoming more careful now.
Negative.
Negative. Okay. Positive? Anyone? No. Okay. Yeah. So actually here it's going to be negative. So everywhere to this side of the green curve you will have dV dt negative, and here you will have dV dt positive. Okay. All right. So now that we know which way our arrows are directed, how does that help us? Notice that when you have one arrow along the u direction and one arrow along the v direction, then by doing vector addition you can actually find out which way you would be flowing. Okay. So at each point I can now do vector summation of these u and v arrows. So you would say that, okay, take any point here, let us say take this point. Here u has a flow in this direction and v has a flow in this direction, so I should be flowing in this direction. Okay. Now there is something additional. See, epsilon had completely disappeared from our analysis altogether. Okay. So now what role does epsilon play? It makes, yeah, so it makes the, whenever you are not on this curve, on the du dt equal to 0 curve, it will make v very, very small, because you are multiplying dv dt, the right hand side of dv dt, by epsilon, right, which is very, very less than 1, 0.001. So effectively, you know, imagine it's something value very, very close to 0. So unless you are exactly on this curve, whenever you are here, u contribution is much bigger than the v contribution. Okay. And so u contribution will dominate. So if you are here, for example, out of this thing, you will be here immediately flowing here, the v direction actually does not matter much. Okay. Similarly, if you are here, you will just immediately flow. So if you are anywhere here, you are just flowing immediately here, because the v contribution is very low, whereas if you are here, you are immediately flowing here. Okay. Now suppose you start with v equal to 0, u is some value which is less than alpha. What will happen? You will flow back to the resting state. But suppose you are here, you are going to flow to this point. Okay. You can't cross this, because the moment you cross this, what happens? The u direction will flip and you will be pushed back to this curve. Okay. So far so good, you already know this, right, that it will flow here. Now what will happen? Once you are on this, u contribution goes away and the v part becomes important. And what is v here, dv dt? Everywhere to this side, dv dt is positive. Okay. So that means it will push you along this curve, right. You are on this curve because du dt equal to 0, you have no option but to stay on this curve. Okay. But on this curve you will be pushed to the top because dv dt is still not 0. Okay. So you will be pushed. Okay. You get pushed, let us say you reach this point. After that, what will happen? Can you go down? You can't go down because dv dt is telling you should go up. Okay. So you are in conflict with that. And so this struggle between u and v pushes it out of this curve. The moment you get pushed out of this curve, what will happen is u takes over. Okay. And you flow all the way here until you hit this u null line once more. Once you hit the u null line, what happens? The u contribution disappears, the v contribution now takes over. Now which way is v pointed? Down. And so you will flow down this until you reach back the resting state. Okay. So this is your trajectory when your stimulus is bigger than the threshold. Initially you get pushed away from the resting state, but you do a long excursion and eventually come back to your resting state. Okay. Okay. It's like you know, with lots of struggle you manage to get across the US-Mexico border, then Trump catches you and you are sent back home after a long excursion. Sorry for that poor joke. Okay. So this is just, you know, to show you what happens. So below threshold you decay to the resting state, above the threshold you have a long excursion and then eventually you go back to the resting state. Okay. In both cases the end result is the same, but in one case you immediately are going back to the resting state, in another case you are giving a very long first your U increases by a large amount, the excitation increases by a large amount before it is decaying back to the resting state. So how will this look if you look at it in terms of time? Okay. So how will U versus T look? Remember this is in UV space. How will U versus T look like? Yeah.
I mean, he's still pointing upwards, right? We got.
Yeah. So when it gets pushed out of the curve here, you mean here, right?
Right.
Yeah. That's because epsilon is so small that U is the dominant contribution. There is a very small nudge maybe which is slightly above, but U moves so fast that before it has sufficiently moved up, it has reached this curve, okay, where it is basically pushed back. Okay. So how will U versus T look like? So first I will put a alpha here. Okay. So if you are less than alpha, suppose you are starting here, what will it look like? Exponential decay back to 0, correct. If you are here, what will it look like? It shoots up and okay. So now remember, this happens very fast compared to this. So time is very important, right? So what will happen is it has a almost vertical rise up to this point. Okay. So very steep curve. So it steeply goes up. Okay. Now at this point it's moving very slowly. So the U is decreasing, but it's decreasing very slowly. Okay. So what will you find? You'll find something which looks like this. It's decreasing, but it's decreasing slowly. Okay. Then once it reaches this point, okay, it decreases very fast. Okay. So you have a almost vertical precipitous fall off, okay, until you reach this point. Remember this is at negative U, right? So you have crossed the 0 line, you have reached negative U, and then slowly you go back to 0, right? And so you will go back to 0 like this. Okay. Yeah, question.
So along that that hike U takes, the particle takes on the right side, du dt is 0.
Yeah.
But U is changing.
But you are on the curve, the U is changing because of the V contribution. Okay. Du dt itself
Yeah.
is 0.
Okay.
Everywhere on this point you are satisfying this condition. V equal to U into E minus alpha is 1.
It's because of that minus V term.
Yeah. Okay. All right. So this, okay. So if this becomes, so if you're looking at it in a very large time scale, and if epsilon is sufficiently small, you will see that it will look like this. And this is the classic what? Action potential. So compared to the width of the action potential or the action potential duration, the time it takes for the neuron to recover back to the resting state is very long, okay, which is essentially one of the basic properties of the neuron. Okay. So we have created a model which essentially captures the action potential starting from just those 3 basic assumptions. Okay. So your model should always have some non-trivial behavior, right? So if your model has everything that you wanted out of the model right at the beginning, you put it there, then it's a kind of a trivial model, right? But here I didn't actually explicitly say that it has to show action potential behavior, but it still managed to show me the action potential. So that's kind of means that the model is actually a non-trivial model. Okay. Okay. So now I said initial condition can cause me to go this way or this way. Now suppose the neuron is in the resting state. How do I make it show me an action potential? So initial condition is 0 0. Noise, but noise is kind of we can't always depend on noise to give us action potential, right? External stimulus. Okay. So how will I put in an external stimulus here? Any ideas?
You need to change.
So I have du dt is equal to u into u minus alpha into 1 minus u minus v, and dv dt equal to epsilon k u minus v. Okay. And I know I can interpret this as membrane potential or a potential, right? Okay. So now can you tell me what do I need to do to introduce external stimulus? Where would external stimulus be added? Which equation? Du dt, right? So plus. So what is this external stimulus going to be? So notice, if this is membrane potential, what is ddt of a potential? dv dt? Yeah, right? So essentially I can think of it as a current. Okay. So this is my stimulus. So this could be either coming from another neuron through synapse or gap junction, or this could be actually I putting a electrode and trying to stimulate it. Now what happens if I introduce this to my null clients? So this is my null clients, right? Now we introduce this I external. What will happen? Yeah, the curve will rise, right? So if it rises sufficiently, you will see that now even at your resting state you will be having a rightward push. So you are here, but since this has been risen, this has been raised, here du dt is positive. Sorry? No, not yet. It's a good point. So this will just give me what? Okay, so this will fly in, okay, and it will come here and settle down here, because I still got a stable fixed point. Okay, but you're right. If I make it even higher, okay, so so suppose I make it even higher such that now it's intersecting here. So now this equilibrium is actually an unstable equilibrium. Now to show that this is unstable is non-trivial. Okay, so if you are trying to think of an intuitive way for me to show this, unfortunately, like the only way I can do is argue about the slope of this relative to this slope. Okay, the real way to show it by is computing the so-called Jacobian. Just believe me for the moment that this is an unstable point. Now if this is unstable, now what will happen? So it cannot now go here because it's going to be pushed out. Okay. So you are going to get settled into what is called a periodic solution, stable periodic solution, or a limit cycle. So it will go round and round. So what you will find is basically a spike train. It's in this direction. Oh, sorry, you are right. Yeah. Sorry, yeah. Okay. And so you will get this spike trains. Okay. As long as you keep the stimulus on, it will generate this series of spikes. Okay. What happens if you make it even higher? You get what is known as tetanic stimulation. The neuron gets stuck at the extreme high membrane potential. Okay. So, yeah. Okay. So this is your U curve. This is your V curve, and you basically, this is just basically a repetition of what I was saying. And if you want to show how this looks like in time, so you can do a 3D plot where you have time along the horizon, one of the horizontal axis, and then in one horizontal axis you plot U, another horizontal axis you plot V, and you notice that you can actually plot the entire trajectory. So this is your stimulus. So at this point you have given a suprathreshold stimulus. So it was in the resting state, and then because of the suprathreshold stimulus, its U is going to increase. So the U is plotted here in red. So it's going to increase, and then it's going to increase the inactivation, and then it's going to decrease its U, okay, and then the V is also going to somewhat decrease, and then slowly it will converge towards 0, 0, back to the resting state. Okay.
Those are the projections on.
Yeah, so this is the U, this is V, this is the phase space. Okay. So this is the UV space, this is U versus T, this is V versus T, and I use the remaining thing to just show you the current, the I external. Okay. Okay, so as I mentioned, this is basically the Fitzhugh-Nagumo model. So this is Richard Fitzhugh. Now he didn't of course start out the way I did. Yeah. Okay.
Just trying to understand the 3D.
Yeah.
So if I kept my current constant, once I increase the current, the red one, and if I kept it constant, I would just get a circle, the square.
Not necessarily. So as I said, that requires a certain range of current where you have made the fixed point unstable. So that you basically make it go through the limit cycle. Below that, it will give you a action potential and settle to a slightly higher resistance state. But I actually have another similar diagram where I show precisely that if you give it a current in that range, how it will go through that series. I think if I'm not mistaken, let me just show you that. Yeah. So if you have increased your current such that your fixed point is an unstable state, you will have this limit cycle, and this is how the 3D diagram is going to look like. Okay. So you keep doing this curves again and again over time. Okay. So just a little bit of history to go back. So Richard Fitzhugh actually got the model not the way I described it, but actually taking Hodgkin-Huxley and simplifying it. Okay. So in case you are wondering, like is, can you really believe Fibonacci model, because I just derived it from these 3 properties, and not using a single iota of biological realism. Don't worry, actually this was originally derived coming from Hodgkin-Huxley. So he basically kept simplifying it until he gets the basic essence. Okay. And Nagumo, Junichi Nagumo, who also around the same time discovered the model, actually wasn't even looking at neuron. He was actually looking at one of the first oscillatory electronic circuits. So using this Esaki diodes, he was trying to build a electronic circuit which can give you relaxation oscillations, and he came up almost independently with the same set of equations. Okay. By the way, this is actually this stuff that he used for his experiments is actually still there in University of Tokyo in the museum. Okay, so I just want to end with a very short intro to how to solve Fibonacci. So since I'm out of time, I will just put this slide up, and Shakti will put it up tonight. I have already shared with you the corresponding MATLAB codes. So what you need to do is you need to just go to MATLAB or use Octave if you want. Okay, what happened? Yeah, okay. So when you open MATLAB, this is what the command window looks like. Octave has a similar thing. Okay, so so if you have fhn.m, that code that I told you, so if you open it in your so this is the editor of the code. So you will see that it has a time increment, that is I'm using a simple Euler method. I've given the threshold, that is alpha as 0.3. I'm using the slope k as 1, and I'm using an epsilon of 0.01. I'm giving a very small external current, let's say 0.05, okay, and I'm going to run it for 50,000 iterations. So if you want it in real time, it's 50,000 into delta t 0.01. So basically it's 500 time units. Okay, all right, so I run it, okay, and it will plot the u and the v curve, and you can experiment with what would happen if I change my threshold, what will happen if I change my k, what would happen if I change my epsilon, what will happen if I change my external current, and so on. The other thing I have is the phase plane diagram. Okay, so here again I have changed my threshold to 0.1, my k is 1, epsilon is 0.01, and current is 0.05. So if I run it, it will show you the UV diagram along with the vectors which are pointed in corresponding directions. So if you want, you can even plot the trajectory of the neuron on this. Okay, all right, and I have something else which is I also shared something else which is like the propagation of a spike along an neuron. So this is using the so-called cable equation. So I didn't get time to look into it, but hopefully I'll be able to cover a bit of it tomorrow. So basically what we'll find is that how does the action potential actually propagate along the axon, okay, and I can model it using a spatially extended model of the neuron. So for this I will have to use a model yeah. Yeah, so I'll be using this FHN chain. Now in the FHN chain, if I run it, you will see that it gives you 2 plots. So this is it's a chain of 100 elements. So each of the elements is excitable. So think of it as basically your axon, and this is time. And so what you're seeing is basically a space-time plot of an action potential propagation. So if you want to see it in 3D, this curve shows you the u curve, the excitation variable, and this is your what do you call space, and what you're seeing along this axis is time. So basically you see that this pulse is actually propagating along, so time is increasing along the, you know, from bottom to top. So it's actually propagating from one end to the other end, okay, and this is the profile of the excitation variable at every point in space and time as it propagates from the left end to the right end. Okay. So again, you can experiment with your axonal conductance. So if you open the code, you will find that the axonal conductance is given as a diffusion constant. So you can see, like, you know, if you change it, will it slow down? You know, how does the axonal conductance affect the speed of the action potential propagation and so on. So you can try out all these experiments.